So today I will speak about the LP spaces. So remember from the last lecture that if I have a function f defined in omega and taking value in the extended line, we defined a norm fp, which is the integral on omega of f d mu, where we take f, the norm of f to the power p, and we take 1 over p, and here p will be a number between 1 and plus infinity. So LP will be the space of functions for which this norm is finite. So LP will be the space of functions from omega to the extended line such that fp is finite. And we have seen in the last lecture that LP is a linear space, in the sense that if I take alpha, a real number, and two functions f and g in LP, then alpha f plus g is a function in LP. Now, what we will do today is to define a distance using this norm in this space LP, and to show that LP is complete with respect to this distance. And then we will discuss the convergence in LP induced by this distance and compare this convergence with almost sure convergence and convergence in measure. So let's define a distance in LP. So the distance between f and g will be given by f minus g norm p. So what I claim is that this defines a distance, and this is clear because, well, if dfg is equal to 0, this means that the integral of f minus g p d mu is equal to 0, which means that f is equal to g almost surely, which means that f and g belong to the same equivalent class so that they are equal. It's also clear that this distance is symmetric, that the distance from f to g is equal to the distance from g to f. And finally, we have the triangle inequality. I claim that the distance from f to h it's less than or equal to the distance from f to g plus the distance from g to h. And why this is true? Well, this is a consequence of Minkowski inequality, which we proved in the last lecture. So let's take the distance between f and h. This is the norm p of f minus h. I can add and subtract the function g, and then so we write this as f minus g minus h minus g in the norm p. Now by Minkowski inequality, this is less than or equal to f minus g p plus h minus g p, and this is exactly the distance between f and g, and here the distance between g and h. So this inequality, it's a simple consequence of Minkowski inequality, and therefore d defined by this identity, it's a distance in the space LP. Just note here that in the space LP, I mean, two functions which are equivalent are in the space LP considered to be equal. We are LP, it's in fact defined on M, so the space of equivalent classes. So now we will introduce a topology. We'll say that a sequence of functions fn in LP converge to a function f in LP if and only if the norm of the distance converge to 0. So this is a definition. So it's a new concept of convergence, and that convergence will be represented by this symbol LP. Now, of course, we would like to compare convergence in measure with convergence in LP, convergence in almost surely. But before that, let me give you two examples to fix ideas about this convergence, and then I will show that the space LP is complete. So it's always very good to have examples in mind when we discuss convergence. So let me take here an example of, let's say, functions which between 0 and 1 over n are equal to n to the power 1 over p. Right? So this is the function fn. In the interval 0, 1, n, 1 over n, it's equal to n to the power 1 over p, while it is 0 everywhere else, and these are functions defined on the line. So, well, it's clear that this function fn, it's converging to 0 almost surely. Right? Because, well, for every point different from 0, this function, it's equal to this sequence, it's equal to 0 for n sufficiently large. And, well, it also converges to 0 in measure. But if you now consider fn minus 0 p, and let me take power p, so this is equal to fn to the power p. Of course, we are here considering the Lebesgue measure. Well, this is equal to, well, this function is 0 outside the interval 0, 1 over n, and on the interval 0, 1 over n, it's equal to n to the power 1 over p. So this is equal to 1. So here we have an example of a sequence which converges to 0 almost surely in measure, but which doesn't converge to 0 in LP because, well, this difference is constant equal to 1. A second example, it's similar to the previous one, but now we'll take a function which in the interval 0, n, it's equal to 1 over n to the power 1 over p. So now, well, this function, this sequence, let's call this sequence gn, so let's call that function gn. So this function gn, it's equal to 0 outside the interval 0, n, and on the interval 0, n, it is constant equal to 1 divided by n to the power 1 over p. So, well, it's clear that this function gn, it's converging to 0 uniformly, right? Because whatever on the line, whatever epsilon you fix, there is an n sufficiently large for which gn it's bounded above by epsilon. Well, it also converge to 0 in measure because, well, for the same reasons. While if you now again compute gn minus 0 in the norm p at power p, this is equal to the integral of gn to the power p d lambda. Here again, I'm considering the Lebesgue measure. Well, but this integral, well, it's very easy to compute. You have to consider the integral from 0 to n. There, gn is constant. If you take power p of that, that will be 1 over n, and this is integrated on an interval of size n. So this is again equal to 1. And here we have a second example of a sequence which converges to 0 uniformly, but which does not converge to 0 in LP. So these are two examples when we will be discussing if convergence in measure to, if a sequence converges to a function in measure, well, does it converge in LP? We have here two examples which says it doesn't, so we'll need to impose extra conditions on the sequence in order to guarantee convergence in LP. But before I do that, let me show that the space LP is complete. So you probably know what Cauchy sequence is, but let me define it since we didn't mention this concept before in these lectures. So I will say that if I have a sequence Fn of functions, Fn in LP, I will say that Fn, it's a Cauchy sequence if for any epsilon positive I can find n naught such that if n and m are larger than n naught, then Fn minus Fm, so this is m non-p, it's less than or equal to epsilon. So this is what is a Cauchy sequence in LP. And the theorem I want to prove reads as follows. Well, assume that the sequence Fn is Cauchy in LP, of course. Then there exists a function. So this is a sequence. I didn't write it, but I said it. It's a sequence in LP. It's Cauchy in LP. And what I claim is that, well, if it is Cauchy, there exists a function f in LP such that Fn is converging to f in LP. And this is what we call complete. So we are proving that the space LP is complete. In other words, that any Cauchy sequence converges. So this is what I will prove now. So let's prove this theorem. So we have a sequence, our assumption is that we have a sequence Fn of functions in LP and that this sequence is Cauchy. In LP. And we want to show that there exists a function f in LP such that Fn converges to f in LP. So the proof is divided in several steps. The first step will be to construct the function f. And for that, the main idea will be to show that we can construct a subsequence here nk and a set f such that the measure of f complement is 0 and that f nk of x it's Cauchy on f, which means that for all points x in f, the sequence f and kx is Cauchy. Since it's Cauchy and any Cauchy sequence on R converges, we'll know that f and kx converge. I will represent by f of x the limit. So for any point x of f and kx converge to what we're calling fx, and therefore that this subsequence is in fact converging almost surely to a function f. So this is our first step. We want to construct this function f by using the fact that Cauchy sequence on R converge. So by assumption, we know that Fn is Cauchy in LP. So let me write what does that mean. That means that for any epsilon positive, I can find n0 such that if n and m are larger or equal than n0, then fn minus fm in the norm p, it's bounded by epsilon. Of course, I can here, instead of taking the norm, taking the pth power of this norm, I'm just replacing here epsilon by epsilon to the power 1 over p. So what I will now do is I will choose a sequence and apply this assumption. So let me take epsilon, a sequence of epsilon. So let me take epsilon k to be 1 divided by 2 to the power k times 2 to the power k, and we will see afterwards why I'm choosing this special sequence. So by taking this special epsilon, what I find is that there exists nk, such that if n and m are larger than nk, then fn minus fm norm p at power p, it's bounded by our epsilon k, which is 1 to k times 2k. Well, so if I take k equal to 1, I get n1, for which this holds for all n and m larger than n1. Then I take k equal to 2, and I find n2. Of course, any number larger or equal than n2 will also satisfy this property. So by that, I just want to claim that I can choose this sequence nk strictly increasing. So I can assume without loss of generality that this sequence nk is strictly increasing. Because, well, if I choose n1, n2 up to nk, then I just apply the hypothesis to epsilon k plus 1. I find nk plus 1. If nk plus 1 turns out to be smaller than nk, I can, of course, change the value of nk plus 1 to make it larger than nk. So I can assume without loss of generality that this sequence nk is strictly increasing. Okay. And this tells me also that for that sequence, since it is strictly increasing, I can take here n to be equal to nk and m to be equal to nk plus 1. So what I have is that nk minus f nk plus 1 to the power p, it's bounded by 1 over 2k to k. Right, now we'll start to construct our set F. And in this set F, I want the difference between f and kx and f and k plus 1x to be small. So let me erase the first few lines to continue the proof in this blackboard. So now, what I claim is that I can estimate the measure of the sets of points for which f and k, so this is the set of points x, such that f and kx minus f and k plus 1x, it's larger than 1 over 2 to the power k. And let me put it here at p maybe. So, well, I can rewrite that as the integral over the set, so the set of points f such that f and k minus f and k plus 1 to the power p, it's larger than 1 to the 2k d mu. And maybe I'll have to change, well, I don't like that p here very much, so let me erase it, and maybe I'll have to change the definition of our epsilon k, we'll see that in a second. Okay, so for the moment we just write the measure of this set as the integral over the set of the function 1. You see that on the set 1, it's bounded below by 2 to the power k times this difference. So this integral, since 1, it's clearly bounded above by 2 to the power k, and let's take a power here, so I get here 2 to the power kp times f and k minus f and k plus 1 to the power p d mu, and I'm still integrating over this set. Okay, so this inequality follows just from the fact that 1, it's bounded by 2 to the power k times this difference, so it's also bounded by this expression at the power p, and this is what I estimate. I estimate 1 by this expression, and I'm still integrating over this set. But now, since this expression is positive, I can just remove the restriction to that set and get a new inequality for which it follows that this expression is bounded by that one. So here, I made a mistake by choosing this sequence. I would prefer to take epsilon k as 2 to the power k times 2 to the power k times p. And so you can check back that everything I said for my sequence epsilon k goes true if I take this new sequence epsilon k, in which I replace 2k by 2 to the power k times p. And why I want to do that? Well, I want to do that because, well, this is equal to 2kp times this integral, but this integral is exactly f and k minus f and k plus 1 to the power norm p to the power p, which is bounded by this expression. So it follows from our construction that this integral, this 2 to the power kp will cancel with this 2 to the power kp, and I will get here 1 over 2k. Okay, and this is what I wanted. I wanted this expression to be bounded by 1 to the power 2k, and this is what we proved up to this point. So let me summarize what we did. We construct a sequence nk, which is, so this is a subsequence which is strictly increasing, and for which we know that the measure of this set is bounded by 1 to divided by 2 to the power k. So now let me erase these lines and continue the proof. So remember, our goal is to construct a set F. Now at this point we will use a very canonical estimate. I will take the union of these sets. So I'll take the union over all k larger than m of f n k minus f n k plus 1, so these sets, which is larger than 1 over 2k. So these are the sets of points, exactly these sets, and I'm taking the measure of the union of these sets. So I'll bound that by the sum of the measures, and this will give me a 2 to the power m times 2. So I have this estimate. Now I can take the intersection over all m, and this will be my set F. So the set F will be the set of points x, or the intersection for m. So this is F complement, in fact, of intersection of m larger than 1, union k larger or equal than m of the set of points x, such that f and k of x minus f and k plus 1 of x, it's larger or equal than 1 to the power 2k. And this is our set F complement. So it follows from this estimate that the measure of f complement is the measure of this intersection. So it's, of course, smaller or equal than the measure of this set for any m, which is bounded by 2 divided by 2 to the power m. So the measure of f complement, it's equal to 0. So this was one of the first property we wanted about this set f. Now what I claim is that the sequence f and k, so I don't need these lines anymore. So now my claim is that the sequence f and kx is Cauchy. So if I take any x in f, what I claim is that this sequence, which is a sequence of real number, is Cauchy. And well, so let's take a point x in f. But what is the function f? We have here f complement. So let's take the complement of this set. This is the union of the intersection of all points y, such that the complement of this set is the set of all f and ky minus f and k plus 1 y, and this is bounded by 1 over 2k. Okay? So this is the set f. Well, so let's take a point x in this set. Since f belongs to this union, it must belong to some of these sets. So there exists some m such that x belongs to the intersection for k larger than m of set of points y, such that f and ky minus f and k plus 1 y, it's smaller than 1 over 2k. So our point x belongs to this intersection, so it means that it belongs to all of these sets. And since it belongs to all of these sets, this means that f n k x minus f n k plus 1 of x, it's less or equal than 1 over 2k for all k larger than m. And now by using a triangle inequality, we can obtain that if you take a k which is larger than m, and if you take a j which is larger than k, then by writing this difference f and j x minus f and k of x, I can rewrite this by introducing all intermediate terms. So, well, let me write it as a sum from going from k to j minus 1 of f n I plus 1 x minus f n I x. And this is now bound. So this difference, it's bounded by 1 over 2 to the power I. And since I'm summing, this is bounded by 1 over 2 times 2 to the power, the smaller one, k. And therefore, we just proved that for any j larger than k, this difference is bounded by 1 over, there is a 2 above and not below, 2 divided by 2 to the power k. And of course, it follows from this estimate that the sequence f and k x is Cauchy, because, well, give me a delta positive, I can find a k larger than m, such that 2 divided by 2k, it's smaller than delta, and therefore for any k and j, so let me call that k0, such that k0, so now given that k0, if I take any j and k which are larger than k0, they are also larger than m, because k0 is larger than m. And for this j and k, this difference is bounded by 2 divided by 2k, but k is larger than k0, so it's also bounded by delta, which proves that this sequence is a Cauchy sequence. So we proved the claim that f and kx, it's a Cauchy sequence for any point x in f. Okay, so let me summarize what we did up to now. Okay, so let me erase that. So up to now, we proved that the existence of a subsequence nk, which is increasing, and the existence of a set f in the sigma algebra, right, such that mu of f complement is 0, and for any x in f, the sequence f and kx is Cauchy. So this is what we proved up to now, right? That we have a measurable set f and a subsequence nk, such that the measure of f complement is 0, and such that for any x in this set f, the sequence f and kx is a Cauchy sequence. So this is a sequence of real numbers. So since we know that for Cauchy sequence of real numbers, we know that they converge. We know that f and kx, so for any x in f, we know that f and kx converge. Okay, so let me call the limit fx. So from that, we obtained immediately that f and k, it's converging almost surely to this function f. Of course, up to this point, f is defined only on the set f, but I can set f of x to be equal to 0 if x does not belong to the set f. This set, this function f, well, with that definition, it's clear that the sequence f and k is converging almost surely to f, which is now defined on all omega. Well, because f and kx is converging to f of x for any point x in f, and the measure of f complement is equal to 0. Since f and k is converging to f almost surely, it means that f is measurable. So, from our claims, we have now a function f, which is defined on all omega, taking value in the extended line, and we have a subsequence f and k, such that f and k is converging to f almost surely. So this is our candidate. So at this point, we concluded step 1. Step 1 was consisting in finding this function f, which is our candidate as limit of this sequence f and k in LP. Right? So I hope that you all understood how we construct this function f by using the fact that Cauchy sequence of real numbers have limits. So this is the conclusion of the first step. So now, in our second step, so let me just recall step 1. So step 1, at the end of step 1, we concluded that there exists a subsequence nk and a function f, which is measurable, such that f and k, it's converging to f almost surely. Now, what I claim in step 2 is that this function f belongs to LP. So let's prove that f belongs to LP? Well, what we know is that f and k belongs to LP and that it converges almost surely to f. So remember that, well, since f and k is converging to f, there exists a set f such that mu of f complement it's equal to 0, and f and k x it's converging to f of x for all x in f. So our proof will be based on that. But before we prove, what I claim is that the sequence fn p is bounded. So there exists a constant c such that f and p is bounded by c for all n. And this is very simple, just follows from the fact that this sequence is Cauchy in LP. Well, since it's Cauchy in LP, let's take epsilon equal to 1. By taking epsilon equal to 1, we know that there exists n0 such that for all n and m larger than n0, fn minus fm p it's bounded by epsilon, but epsilon it's equal to 1. Right, now let's take n larger than n0, that n0 which we found, fn norm p, I can rewrite that as fn minus fn0 plus fn0 p. Then use the triangle inequality, and on the one hand I will have this difference, but since n and n0 are larger than n0, this first difference is bounded by 1, so this is bounded by 1 plus fn0. So here we obtained a uniform bound for fn for all n larger than n0. And since each fn belongs to LP, what we have is that fk, or fj if you prefer, p, it's bounded by the maximum of fi p for p running from, for I running from 1 up to n0 plus 1, right? Because, well, for all j smaller than n0 we have that trivial bound, and for j larger than n0 we have the bound fn0 plus 1. So here is our constant c. This is clearly finite, and we proved, therefore, our claim that this sequence it's of real number, of positive real number, it's bounded. So let me erase the proof of our claim. And now let's prove that f belongs to LP, which is our second step. And this is essentially, well, it's a simple consequence of Fatou lemma, right? So I have that f to the power p d mu. Well, since f complement has measure 0, this is equal to the indicator of the set f times the function f to the power p d mu. Right here I can just, well, the difference between these two integrals is that that one it's integrated only on the set f, while that one it's integrated on omega, but since the set f complement has measure 0, these two integrals are equal. Well, and since we have that limit, it's clear that one f x, and if I take here nk, that this is converging to one fx for all x, right? Because, well, I know that this convergence takes place on the set f, and since this is 0 and this is 0 outside the set f, this is true for any x. So I have a sequence now of functions converging to all points to this function f. I can apply fatu. So fatu tells me that the integral of the limit, it's bounded by the limit inf of the integrals but here again, well, or I can just remove the set f because, well, complement of f has measure 0, so this is in fact equal to the limit inf of f and k to the power p d mu. And we have seen, well, in fact, that these integrals are finite, are uniformly bounded by some constant c. So this limit is bounded by the constant c, which tells us that this integral is bounded by that same constant c, which makes f a function in LP as we claimed. So this concludes the proof of step 2. F, it's indeed a function in LP. Now let's complete the proof. So now step 3. I claim that Fn converges to F in LP. And again, we will use fatu. So fix epsilon positive. Well, this function f, it's the limit of f and k. So I can just repeat what I did to conclude that f minus fn d mu, it's less or equal than the limit in k, to power p, I forgot the power p here, the limit in k of f and k minus fn p d mu. Right, so this is again an application of fatu. Because f and k is converging to f almost surely. Well, I know that the sequence fm is Lipschitz Cauchy. So I know that there exists n0 such that, given that epsilon, such that f a minus fb p d mu, it's bounded by epsilon if a and b are larger than n0. So if this n it's larger than n0, well, since we are taking here the limit in k, for k sufficiently large, nk it's larger than n0. And n, if we take some n, so if we assume that n it's larger than this n0, which is given by the Cauchy property, this expression here, it's bounded by epsilon for all k sufficiently large. So this expression, the limit, is also bounded by epsilon. So what we proved that for any epsilon, we can find n0, which is given by the Cauchy property, such that this difference is bounded by epsilon for all n larger than n0, which means that the sequence fn is converging to f in LP, and this completes the proof of this theorem.